The problem statement from GATE Physics 2017 reads as follows. For the transistor amplifier circuit shown below with R1 equal to 10 kilo ohms, R2 equal to 10 kilo ohms and R3 equal to 10 kilo ohms and beta equal to 99. Neglecting the emitter diode resistance, the input impedance of the amplifier looking into the base for the AC small signal is dash kilo ohms. This is a numerical answer type question and we need to find our answer and then round it off to 2 decimal places and we'll fill in the blank here. So just getting right to the problem. So this is the BJT that's given to us. It's an NPN BJT and it says that this is an amplifier circuit, and for this we have to perform the AC analysis. So how do we go about doing it is that we first need to understand what is the model of a BJT as far as small signal analysis is concerned. So this is the BJT that we have, NPN BJT with collector, base and emitter. The current will flow out of the emitter, DC analysis. So this is the conversion, this is the model that we use that for the small signal analysis. So you can see that the base terminal is over here on the left, the collector is on the right, which is on the top over here, and emitter is at the bottom as always. Now in the question it was given that we can neglect the emitter diode resistance. This means that we can effectively ignore this resistance R pi here. So by ignoring, I mean we assume that this to be 0. So effectively our BJT for small signal analysis can be converted to this. We have assumed R pi equal to 0. So this is the circuit that we finally get. Now what I'll do is that I'll plug in wherever BJT is used. I'll plug in these circuit elements. So everything is a wire except for this dependent current source, because this is a current source as indicated by this arrow. It's dependent. This is dependent on the IB, where beta is the current gain of this transistor, DC current gain of this transistor. Now this was the circuit given to us. So what I'll do, I'll simply replace this BJT with, I'll plug the BJT model that we have developed over here. So I've just done that. So in removing this, so it's R1, R2, VCC, V in all remain the same. R3 also remains the same, and the V out, the port remains the same. Just that base, collector and emitter have been replaced with this. So so now moving forward, this is the after we got this result after the first step. And now the second step is to remove all the independent DC sources. Now remember, I'll point out independent DC sources. So what are the independent DC sources that we have here? So first independent DC source that we have here is this VCC. It's an independent DC source, DC voltage source. So we'll put VCC to ground. By removing, we mean all the independent voltage sources should be grounded, and all independent current sources to be open circuit. So all dependent current source to be open circuit. Now note that this is not an independent current source. This is a dependent current source. See this term here. So this will not be open circuited, right? But VCC, similarly V in is a dependent is an independent voltage source, DC voltage source. So this will also, we can also ground this, right? So what we'll get something like this. So see, VCC is grounded, right? So if we ground VCC like this, so what I've done here is that, so R2 remains the same here, this circuit remains the same. So R1 is between the base, which is this node here, and the ground. VCC is ground. So I've just rather than this leg should be up, I just put it down. Nothing has changed, so everything remains the same. Similarly, this collector will now be grounded because VCC has been grounded, so this remains the same. So this is the circuit that we have gotten. So I'll reiterate that remove independent DC sources means all independent voltage sources to be grounded, just like VCC, and all independent current sources to be open circuited. There are no independent current sources. This is a dependent current source, so nothing will change over here. And this is the circuit that we had. Now at in the third step we'll put a test source. So where we had to put, we had to find the input impedance. So what we'll do, at the base, so this is the base, we'll put a test source. So this is the V test, this is the I test. So we have put a test voltage source, and we'll measure the test current, and we can simply define the input impedance is nothing but V test over I test. So whatever current we are pushing in the denominator, and in the numerator we have the voltage, the AC voltage, small signal AC voltage that we are applying. Now, so this is the final the circuit diagram that we have over here, and these are the constants that were given to us in the problem itself. What we need to find is the input impedance, which is defined at V test over I test. So we'll start with that, and let's just first define a couple of currents which I've defined here. I1 is the current flowing through the resistor R1, I2 is the current flowing through the resistor that we have here R2. Now what I'll do is that, so we'll look carefully and look at this node, the emitter node over here. So this voltage is nothing but V test, right? This is nothing but V test, and this is just a wire, so all the voltages here will be V test. Similarly, this will also be, let's call this for the time being VE. Now first what I'll do is KCL. I'll apply KCL at voltage at node VE. So incoming current is nothing but this IB and IC, right? So I'll write it as IB plus IC is equal to IE. So I'll get IE equal to simply beta plus 1 IB. This is what I'll get. And what I'll do, if I apply Ohm's law across this resistor, right? So I'll write this as well. So I'll write Ohm's law across R3. So I'll write that will be VE minus 0 is equal to IE times R3. And now I know the value of IE, and VE will be nothing but V test. Note that this is just a wire. This over here is just a wire. So VE will be nothing but V test. So I can write V test is equal to IE. The value of IE is nothing but beta plus 1 times IB times 3, right? So this is an expression that we have obtained, and from this I can write IB is equal to V test over beta plus 1 times R3, and let's call this expression 1. Now in step 3, what I'll do is I'll apply KCL at this node. Let's call this as Vn node. KCL at Vn. So we'll put all the incoming current. So incoming current is nothing but I test. So you see, this is the incoming current in the blue that we see here. And the outgoing current is nothing but I1 plus I2 plus IB. So I'll write I1 plus I2 plus IB. So I'll get I test equal to, now I1 is nothing but, so we know that this voltage is nothing but V test. This is a wire. So this will come out to be V test over R1 plus V test over R2, and we know the value of IB from expression 1, which we'll use here. So that will be V test over beta plus 1 times R3, and from this I can get I test is equal to V test should be R1 parallel R2 parallel beta plus 1 times R3, and thus I'll get V test over I test. V test over I test will be nothing but, so sorry, this was V test over this. So V test over I test I'll get is R1 parallel R2 parallel beta plus 1 R3. So this is 10k parallel 10k parallel. So beta is 99, so that will be 100 into R3, that will be 100k. So that will be, if we this 10k parallel 10k is 5k, so 5k parallel 100k. So let me just look into my calculator, and yeah, so this value is coming out to be 4.76 kilo ohms. So this is nothing but V test over I test, nothing but input impedance Zn, right? So we find out Zn equal to 4.76k. Now this is also known as Zn, input impedance. So we just found out that the input impedance is 4.76 kilo ohms, and this is already up to 2 decimal places. So that is all that we had to do. Thank you for listening.